Hello everyone and welcome to class number 33 of Physics 218. Last time we talked about the simple harmonic oscillator in quantum mechanics and talked about the energy eigenfunctions and eigenvalues and how the simple harmonic oscillator is a good model for molecular vibrations. Today we'll introduce ourselves to scattering states in one-dimensional quantum mechanics, and we'll start looking at scattering by a potential energy step. Today is going to be a shorter class than usual, as will Friday, so we'll start this topic today and sort of come at it from a more qualitative and conceptual point of view. We'll save some of the mathematical analysis for Friday's class. I first want to remind us a little bit about what we've done in one-dimensional quantum mechanics so far. So we began by considering the free particle, which has a potential energy of 0 everywhere. And we saw that plane waves, something that goes like, a wave function that goes like e to the ikx minus omega t, is a solution of the full time dependent Schrödinger equation for a free particle. What we can sort of now see, based on what we've learned since then, is that a e to the I k x, right, so just the spatial part of this plane wave is a solution of the time-independent Schrödinger equation. You can see how, right, sort of we have this is really the product of something that depends only on position with something that has an e to the minus I something times t time dependence. So this actually does have the right form as a solution, as a full time dependent solution, where this spatial part satisfies the time independent Schrödinger equation. If you go and plug this in, right, you find that the energy eigenvalue, right, goes like h bar squared k squared over 2m. The critical thing here is that in the case of a free particle, the energy eigenvalues are continuous. Right? E can take on any positive value. The other thing that we've spent a while looking at, right, is bound states, right? So we've looked at things like finite wells and infinite wells, and last time the harmonic oscillator. The key thing that should be pointed out here is that for bound states, right, so whether they're evenly spaced in the harmonic oscillator or not, as they are in the case of a finite square well, right, bound states have discrete energy eigenvalues. So energy are, right, and so what we're going to do today is sort of look at a case, right, that's sort of somewhere in between, I think, these two situations, namely a scattering state. And we can define a scattering state in the following way. So it turns out that a scattering state is 1, so that is sort of neither a free particle nor a bound state. So it's a solution of the time-independent Schrödinger equation where E is larger than the potential energy either as you at either positive infinity or negative infinity. So let me write this as at x at plus infinity or x equals minus infinity. Okay. So what we'll see today is that for this for scattering states, like for a free particle, the energy eigenvalues are again continuous. Energy eigenvalues, which I'll just abbreviate as EEV, are also continuous, like the free particle. But as we think about what the energy eigenfunctions look like for scattering states, it turns out we'll be able to draw on a lot of what we learned about bound states. So this is sort of bringing those two things together. What I'd like you to do now is to take a look at a clicker question as you decide whether or not something is a bound state or a scattering state. So hopefully you've been able to conclude that a particle with the energy shown is in fact in a scattering state, right? And that's because the energy is larger than the potential energy at x equals minus infinity. So rather than dealing with the wonky looking potential energy in the in the clicker question, let's look at the sort of simplest example of a situation where we have a scattering state, and namely a potential energy step. So what we'll consider is the following, right? So we consider a situation where the potential energy is 0 for x less than 0, but for x greater than or equal to 0, the potential energy is a constant v sub naught. Now, what might this physically represent? So, and you know, is this just completely artificial? I would argue that it's not. So, where this might come up, right? You might imagine a situation where you have like a wire that has a work function. So let me try to draw a picture. So imagine we had a sort of a one-dimensional wire that, you know, where it was very long and you had electrons that were basically free to move within the wire. But then the wire like ends at x equals 0. And then to escape from the wire, the electrons need a little bit of extra energy. That's exactly what the work function is. And so you could have a situation like this where, like, to get out of the wire, and then if the electrons are sort of free afterwards, they need this potential energy. They need a little bit of energy to get over this step. You can also design similar things using semiconductors. So if I have a junction between two different semiconductors, I can get something that's not unlike this as well. And so this is not a completely artificial example. Now, how might we go about physically studying or probing a situation like this? Well, there's something that we physicists like to do. Namely, if we're trying to find out something about a physical situation, oftentimes it's helpful to just sort of shoot particles at it. Namely scattering, right? So right, that that's how we particle physicists try to discover new elementary particles at accelerators like the Large Hadron Collider in Europe, right? They're colliding beams of particles and looking at what happens. And so in my lab, right, we often think about what happens when we scatter light off of particles that are sort of orders of magnitude larger, but still the same general idea. You can probe or learn something about a system by looking at how it responds when you launch waves or particles at it. That's exactly what we'll do here. So study this by launching particles at the step. And we don't have to pick a direction, but for now, let's assume that we're launching particles from the left. So I imagine we do something like this, where I'm shooting particles from x equals minus infinity. Now, how do we try to describe this quantum mechanically? You know, right, that from our previous discussion, that if I want to truly represent a localized particle, I need to think about a wave packet, right? Because a plane wave is not normalizable and cannot represent a localized particle. So let's think about what happens to a wave packet that's incident from the left. Now, to gain some intuition about this, rather than try to write the math down, I'm going to have us turn to a PhET simulation, and we'll be able to see exactly what happens when we have an incident wave packet. So this is the quantum tunneling and wave packets PhET. So to get something like what we were talking about, a potential energy step, I can go over here and choose step in this potential drop-down menu. And so what we can see here is that I can change the height of the step by dragging this arrow, or the height on this side with that one, or like where the step happens. So by default, it's going to send in a wave packet incident from the left. As usual, we're plotting the wave function here. Now the real part, I could also turn on the imaginary part if I wanted, and we have the probability density down here. So with these defaults, let's just see what happens if I click play. So what you can see is that at some time after we've sort of started things off, right, there's some probability for measuring my particle to be to the right of x equals 0, but there's also some probability for my particle to be found to the left of x equals 0. If we let time sort of keep going, right, eventually things get really smeared out, which is really just saying that eventually we have sort of very little idea of where the particle is. But the key takeaway is that, we send a particle in from the left, but we don't know that we're always going to find the particle sort of having gone in the direction that we wanted it to go. We launched it, we could well find the particle somewhere even to the left of where it initially began. Let me reset time here, and you can go and play around with things like we could, for instance, change the initial location of the wave packet, which doesn't change a great deal. We could also change the width of the wave packet. So if I make it wider like this, we can sort of see what happens there. Same general thing, right? There's some probability that we find the particles that are transmitted here and reflected back from my step. Now notice one thing about this, right? Notice that the total energy up here is smeared out. That's because, as we might remember, a wave packet is not a plane wave, right? It is not a wave packet. It does not have a single well-defined energy. In other words, wave packets are not energy eigenfunctions. And so, when we come back to the board, we'll see why we might sometimes want to think of things in terms of plane waves rather than wave packets. So wave packets, as we know, can represent particles, but they're also hard to work with mathematically because a wave packet is a superposition of many plane waves, or an infinite number of plane waves, rather. So we can model particle as wave packet, but wave packet's hard to deal with. One reason wave packets are harder to deal with, right, is that they are not energy eigenfunctions. They are not solutions to the time-independent Schrodinger equation that have a definite energy eigenvalue. So not energy because of this, right, it turns out to be mathematically a lot easier to think about what happens to plane waves. So as we'll be able to see in the simulation, and we'll look at quantitatively on Friday, plane waves are, in fact, solutions of the time-independent Schrodinger equation. They are energy eigenfunctions, and, right, if we ever needed to think about a wave packet, we can always build up a wave packet by superposing plane waves. So we don't really lose anything by thinking about a plane wave, and if you want to think about it that way, you can always think of a plane wave as a model for a beam of particles that all have the same energy. And so we'll just analyze plane wave states and what happens when we have a plane wave incident from the left. At this point, I'll have us return to the PhET simulation and we'll look at a plane wave. So now let's see what happens when we have an incident plane wave. Once again, we're going to send in our plane wave incident from the left, and we're going to start with the total energy of this plane wave larger than V naught. One thing I want to point out, right now we're seeing the total wave function here, but I can also separate this into an incident and reflected piece on the left. But let's start with the sum, and let's watch what happens. So you can see that the wave function is evolving in time, or at least the real part of it is, and the imaginary part is also evolving, right? And however, and this is just like what we've seen with the real and the imaginary part of the wave function in, say, like a bound state. However, notice that the probability density is constant, right? This is a stationary state or an energy eigenfunction. And we can also see that here, right? The total energy is well defined. So there is an energy eigenvalue for this wave function. So when we analyze this mathematically on Friday, we'll focus more on like the behavior at t equals 0, like right here, and figuring out how to sort of analyze what's going on. But now let me just play this for you again. And what I want to show you this time is how you can separate the waves over here into a part that's incident, transmitted over here, and then reflected over there. And so you've got your incident and transmitted portions moving to the right, and the reflected portion moving to the left. So as we'll see, this turns out to be a pretty general property of wave behavior. So things get interesting if we change the total energy here. So if I crank the energy up, we can sort of watch what happens. And I'll switch this back to summing mode. And so if I one of the things to notice is that notice how there's a wavelength change here, right? Sort of these peaks are closer together than the peaks are over here. Hopefully this isn't too surprising from your study of how bound state energy eigenfunctions behave qualitatively. Even though this isn't a bound state, it's still the case that, right, as the difference between my total energy and my potential energy gets smaller, my wavelength increases. So if I drag this down, right, I can sort of make that effect even more dramatic, right? And we have now sort of quite a large wavelength over here where the total energy is just barely larger than my potential energy. Another thing we might observe is what happens if I drag this below my total energy. So now my total energy is less than V naught. Again, we see this sort of oscillation over here, and again, we can think of this as now, right, there's some incident wave and some reflected wave. What we'll notice if I reset time is that now, right, over here in this classically forbidden region where my total energy is less than V, right, notice how this wave function decays sort of, it looks like it might be exponentially into the forbidden region. And hopefully that's something that's not so surprising based on our study of the qualitative features of bound state energy eigenfunctions. Now at this point, I'd like to pause, and I'd like to ask you to think about a whiteboard question, and to make a prediction as to what will happen if I lower the energy a little bit more. So take a moment to think about it, sketch it. I would suggest that you fire up this PhET and see if your prediction is correct, and then we'll come back together. Welcome back. So let's see what happens as we lower the total energy. As we do that, aha! So here in the forbidden region, right, we have sort of less penetration, right? It looks like the wave function decays to zero over a shorter distance than it did before. The other thing to notice is what happens with the wavelength over here. We've lengthened the wavelength, right, because now the difference between the total energy and the potential energy is smaller. So let me slide that back up, right, so you can see what happened. So as we lower the energy, right, we get a longer wavelength on the left here and a shorter penetration distance here on the right. So when we have a plane wave incident on a potential energy step like this from the left, what we've seen in summary is that some of that incident plane wave is reflected, and some of it is either going to be like transmitted as a wave, if E is larger than V naught, or if E is less than V naught, you get sort of this decaying penetration into the region X greater than 0. Now, you might be wondering, is this sort of a property of quantum mechanics? Well, I would argue that this behavior, where something funky, where you have both reflection and transmission of a wave, is actually a common property of waves whenever you have a discontinuity in the medium. So let me actually switch to my computer again, and I'll show you another animation of what happens when you have a wave that encounters a string with a discontinuity. So what I wanted to show you here is how you get sort of reflection and transmission behavior anytime you have a discontinuity in the medium that a wave is propagating in. And a really good example of that are waves on a string. I think there's a picture of this in the Knight textbook you used in 217. This is not, unfortunately, this is not an interactive animation. But what we have here is we sort of have a wave pulse that's incident from the left on a string where there's, on the left side of the string up here, the string has a lower mass density and a higher mass density on the right. So when we send in that pulse, right, what you can see is that part of the pulse is transmitted and part of the pulse is reflected. Same thing happens over here where we've sort of reversed the order and we have the wave pulse incident from the higher density lower speed side. So again, some of it's transmitted, some of it's reflected. One difference you might notice is that like the reflected pulse gets inverted in this case relative to that, and doesn't in this case when we're going from high density to lower density. And so you can actually calculate like exactly how this happens using very similar techniques involving applying a boundary condition, as we'll talk about in class on Friday. Another example of this sort of behavior, this sort of general behavior that you always have reflection and transmission when there's some sort of discontinuity in what the wave is propagating in, comes from thinking about light as a wave. So if you think about light as a classical electromagnetic wave, and think about a situation where there's a medium discontinuity, aka a change in refractive index. So if you go and look out a window, right? So there's air between you and the window is probably made out of glass. Well, you know that you can see out a window, right? So there's definitely some transmission of light from air to glass. However, especially if you sort of wait until it gets dark in the evening, you probably also know that you can see your own reflection in a glass mirror. Not in a glass window, I'm sorry, as though it were a mirror, right? And that reflection is granted faint, which is why you're not going to be able to probably see that reflection like in bright daylight. But the reflection is there, right? So that glass window, at that air to glass discontinuity, does reflect some of the light that's incident on it, even as most of the light ends up getting transmitted through. And if you take upper level E&M, you might work through some of the theory of that and sort of apply the right boundary conditions to Maxwell's equations, and you can sort of work out exactly, based on the material properties, how much of the light is reflected versus transmitted. But again, my point is that this is really just a general feature of wave physics in general, and not really anything that's peculiar to quantum mechanics. So today we've, I think, gotten a good basic overview of what happens in a scattering situation with the potential energy step. Now that we know what sort of phenomena we're looking out for, on Friday we will turn to the mathematical analysis of this and try to see where some of the results we saw in the PhET simulation actually come from. See you then.